Hello, my dear students. Hope all of you are fine and safe at home. Once again, welcome to our online physics classroom. In the previous session, we have gone through magnetic field due to a current carrying circular loop. I hope all of you might have understood the pattern of magnetic field lines around a current carrying circular loop. Today, we will discuss about the magnetic field around a current carrying solenoid. Here we focus on three questions. What is the pattern of magnetic field lines around a solenoid? That will be our first point of discussion. Second question is that can a solenoid be considered as a bar magnet? And third question is that if so, how will you identify its north pole and south pole? Don't worry children, you can answer all these questions after this session. So just hold on to it. Let's get started with today's session. Children, first let's discuss what is a solenoid. Can you see a figure on the screen? So this is a solenoid. Take a copper wire and just wound it in the form of a coil like this. It forms a solenoid and its length will be always greater than the diameter of the coil. So how will you define a solenoid? Solenoid is a coil of many circular turns of insulated copper wire wrapped closely in the shape of a cylinder. So if you connect the ends of the solenoid to a battery like this, and when the circuit is switched on, current flows from the positive terminal to the negative terminal of the battery. Okay. So whenever current flows through a conducting wire, it behaves like a magnet and generates a magnetic field around it. Since solenoid is also made of a conducting wire, when current flows through the solenoid, it behaves like a magnet and generates a magnetic field as said by the famous scientist Hans Christian Ørsted. So what will be the pattern of this magnetic field around the solenoid? You may think it's a little bit complex. No children, let me make it simple to you. Okay, so to make it simple, we need to divide solenoid into small circular coils. So that's what we are going to do next. So we have divided our solenoid into small circular coils. So why do we need to do all these things? Because if you observe a solenoid closely, we can see solenoid is nothing but a series of circles or circular coils joined together in the form of helix. And the pattern or that shape of that solenoid is known as the helical structure. Okay. So when current passes through this solenoid, current is passing through each of these circular coils. So this current carrying circular loop behaves like a magnet. And what is the pattern of the magnetic field around a current carrying circular loop? Just recall our previous sessions. In our previous session, we had discussed about the magnetic field around a current carrying circular loop. So when current passes through each of the circular loops or circular coils, you will get a concentric circles like this. This will be the pattern of the magnetic field due to each current carrying circular loop. Okay, on diametrically opposite sides we have concentric circles like this, and at the same time on each part of the circular coil we have a concentric circles like this, because we consider each segment of the circular coil as a current carrying straight conductor. Okay, and for our convenience, I'm not representing the magnetic field patterns around each and every point. Okay, and all these concentric circles join together to form a large circle like this. See, because a solenoid consists of a series of circular coils joined together. So the resultant magnetic field due to a solenoid will be the combined effect of magnetic field produced by each of this current carrying circular loops. So just combine the magnetic field of all the circular loops. So you will get a large closed loop like this. And if we join this particular concentric circle, this circle, you will get a closed loop like this. And if you join this particular circle, you will get a closed loop like this. Okay, so what is the actual pattern of the magnetic field in a current carrying solenoid? Actually, the magnetic fields of all circles combine together to form a resultant magnetic field. Okay, so finally, the magnetic field around a current carrying solenoid looks like this. Have you seen such a pattern before? Yes, you are right in the case of bar magnet. Isn't it that amazing, children? The magnetic field due to a current carrying solenoid resembles that of a bar magnet. But in bar magnet, we don't have any confusion because we can easily identify the north pole and south pole of a bar magnet. But at the same time, it's very difficult to identify the north and south pole in a solenoid because we don't know which is the north pole, which is the south pole. So our next topic of discussion will be that how can we identify the north and south pole of a magnet? Sorry, not magnet, of a current carrying solenoid. So for that, we can come back to this figure. So in order to identify the north pole and south pole of a solenoid, we can come back to this figure. Here, the solenoid in the figure is connected to a battery. When the circuit is switched on, current flows from the positive to negative terminal of the circuit. And on this side, that means on the left side, this is the direction of current flow. And what is the direction of current flow through that phase of the circular coil? Is it clockwise or anti-clockwise? Just try to view the solenoid from this direction. If you view this particular face of the solenoid from this direction, that means from the left side, what is the direction of current flow through this particular circular coil? Yes, this will be the direction, right? This is the direction. And what is this direction? This is the direction. And what is the direction? Clockwise direction, right? So if current passing through a circular coil is in clockwise direction, then what is the polarity of the face of that circular coil? Is it a south pole or north pole? Children, please recall the clock face rule that we had discussed in our previous session. Do you remember that rule? What was the rule? Whenever current passes through the circular coil in clockwise direction, the face of the circular coil acts like a south pole. And you remember, do you remember this tip? Yes. If you write yes, just extend this S like this, you will get the direction. What is the direction? It's a clockwise direction. So, in this case, left end of the solenoid behaves like a south pole. So, try to view the solenoid from the right side. Okay, children, never try to view the solenoid from the front side of the screen. Try to view this face of the solenoid from the right side. So, what will be the direction of the current flow? Yes, you will get the direction of current flow like this. This will be the direction of current flow. And what is that direction? Yes, this is anti-clockwise direction. So whenever current flows in the anti-clockwise direction through a circular coil, that face will act like a north pole. Okay, so this end of the solenoid acts like a north pole. Now, the problem is solved. We can easily identify the south pole and north pole of a solenoid. Apart from this, with the help of bar magnet also, you can identify the north pole and south pole of the solenoid. For that, just bring a bar magnet close to the solenoid. And if this end, that means the south pole of the bar magnet experiences a repulsive force, we can easily arrive at a conclusion that means this end of the solenoid is also south. That's why this south pole is repelling this south pole. On the other hand, if this south pole of the bar magnet experiences an attractive force from this end of the solenoid, we can infer that this end of the solenoid is a north pole. That's why it is attracting the south pole of the bar magnet. So if once we get an idea about the polarity of one end of the solenoid, we can arrive at a conclusion the other end will be its opposite pole. Okay, in this way also we can identify the poles of a solenoid.